In 2019, two of the most precise ways to measure the expansion rate of the universe delivered incompatible answers. One came from the Planck satellite, reading the afterglow of the Big Bang. The other came from local measurements using supernovae and Cepheid stars. Both methods were refined, repeated, and independently verified. They should have converged. Instead, they split apart. This disagreement is called the Hubble tension, and it has not gone away. As instruments improved, the gap became sharper, not smaller. Adjustments to calibration failed to close it. Statistical errors were squeezed. The problem persisted. At a certain point, researchers stopped asking which number was right and started asking why the same universe would tell two different stories. That shift matters now because this is not an isolated glitch. Similar fractures are appearing in other measurements, timelines, and supposedly fixed rules. Each one can be patched in isolation, but together they form a pattern of strain. Not a collapse, not a crisis, but pressure. Pressure on the maps we use to translate observations into reality. This video follows that pressure step by step, from a single measurement that refused to settle, outward into deeper assumptions about time, law, and structure. The question is not whether scientists have lost confidence. It is whether the universe is signaling that our framework is incomplete. If our most trusted tools disagree at the foundation, what happens when we push them further? The Hubble tension is not just a disagreement about speed, it is a disagreement about method. One approach measures the early universe, when matter and radiation were tightly coupled, using the cosmic microwave background. The other measures the late universe, using distances to galaxies nearby. According to the standard model of cosmology, these two views should align once the math is done. They do not. The early universe predicts a slower expansion rate, while the late universe insists it is faster. The difference is small in absolute terms, only a few kilometers per second per megaparsec. But in precision cosmology, that gap is enormous. It sits well outside the margin of error that used to absorb discrepancies like this. Attempts to resolve the mismatch began conservatively. Teams rechecked instrument calibration. They reanalyzed dust interference, lensing effects, and statistical assumptions. Each correction tightened the numbers, but the split remained. The more carefully the data was handled, the more confidently it disagreed. A second fracture appears in measurements of large-scale cosmic structure. Surveys mapping how galaxies cluster across billions of light-years show subtle tensions with predictions. The universe appears slightly smoother or slightly clumpier, depending on which probe is used. Again, the methods are sound, but the outcomes do not line up cleanly. This matters because these structures grow under gravity over time. Their distribution encodes how matter behaves and how space itself responds. When models tuned to one dataset fail to predict another, it suggests something is missing. Not noise, not sloppiness, but a piece of the underlying picture. A third example comes from particle physics, where precision experiments measure the behavior of fundamental particles. The muon, a heavier cousin of the electron, behaves as if it feels forces not fully accounted for. Multiple experiments, using different techniques, point in the same direction. The effect is small, but stubborn. In each case, the pattern repeats. The theory is mature. The instruments are trusted. The math is consistent. Yet reality produces outcomes that lean just far enough away to be uncomfortable. These are not wild anomalies. They are disciplined disagreements. Individually, each tension can be explained away. Collectively, they suggest something else. If baseline measurements, the kind that anchor entire frameworks, refuse to agree, then deeper assumptions are being tested. And that raises a more unsettling question. What happens when time itself becomes the variable under strain? One of the first signs that time might be misbehaving came from galaxies that appeared too early. Observations from deep space telescopes revealed massive, well-organized galaxies forming just a few 100 million years after the Big Bang. According to existing models, there simply was not enough time for that level of structure to emerge. These galaxies were not small or chaotic. They showed clear disks, mature star populations, and chemical complexity. In the standard timeline, such features require long periods of gradual growth. Seeing them so early forces a choice. Either the measurements are misleading or something accelerated the process beyond expectations. A similar tension appears with supermassive black holes, objects with masses millions or billions of times that of the Sun are observed at epochs when the universe was still young. The usual growth mechanisms, slow accretion, and mergers struggle to explain their size. The clocks say there was not enough time. Some researchers propose exotic formation pathways, such as direct collapse from primordial gas clouds. Others suggest periods of rapid growth that current simulations underestimate. Each proposal can ease the tension slightly, but none removes it entirely. The timeline still feels compressed. Closer to home, stars introduce their own temporal paradoxes. The Methuselah star appears older than the universe itself, at least within uncertainty ranges. While errors may resolve the issue, its existence highlights how sensitive cosmic age estimates are. A small shift in assumptions produces a large shift in conclusions. Chemical timelines show similar stress. Certain elements, like lithium, appear in quantities that do not match predictions from early universe chemistry. The discrepancy is persistent and well documented. It suggests either missing processes or an incomplete understanding of early conditions. These are not claims that time is broken in a literal sense. They are signals that our models of growth, sequence, and causality may be stretched beyond their comfort zone. The universe seems to reach complexity faster than expected. When enough events arrive early, maturity stops feeling rare and starts feeling systematic. And if time-based expectations fail at multiple scales, it raises a deeper concern. Perhaps it is not just the timeline that is off, but the rules we assume remain fixed as time passes. Physics rests on the idea that certain quantities do not change. Constants are assumed to be constant, and laws are assumed to apply everywhere in the same way. This assumption is not philosophical, it is practical. Without it, prediction becomes fragile. Yet some observations are quietly testing that stability. One example comes from fine structure measurements of light absorbed by distant galaxies. These spectra encode the value of fundamental constants billions of years ago. Most measurements agree with today's values, but a few analyses hint at tiny variations across space. The effect is controversial, but it refuses to disappear completely. If confirmed, even a minute drift would matter. Chemistry depends on precise balances. Atomic structure depends on fixed ratios. A universe with slightly different constants behaves very differently. That is why these hints attract scrutiny rather than celebration. Another tension appears in particle decay rates. certain rare processes occur more often than predicted, depending on context. The discrepancies are small, hovering near statistical thresholds. Critics argue they may fade with more data. Supporters note that they align across independent experiments. The issue is not that the laws are clearly changing. It is that they appear to strain under close inspection. The same equation fits one regime beautifully and stumbles in another. That pattern invites caution rather than rebellion. Cosmology offers a parallel case with dark energy. Its behavior is often modeled as constant, but some datasets allow room for change over time. A slowly evolving influence would subtly alter expansion history. Again, the data does not demand this, but it allows it. This creates an uncomfortable ambiguity. Either the universe is perfectly consistent and our measurements are brushing against their limits, or the consistency we assume is an approximation. Both options preserve physics, but they imply very different futures for understanding. If rules can bend without breaking, then what we call law may be emergent rather than absolute. And if that is true, the next question follows naturally. What kind of underlying machinery could make stable rules appear and occasionally misbehave? When surface rules begin to strain, scientists look beneath them, not for mysticism, but for structure. One possibility is that the laws we observe are not fundamental, but emergent, like temperature arising from molecular motion, stable most of the time, but imperfect at the edges. In this view, reality operates with deeper constraints that only reveal themselves under extreme conditions. Limits on information, resolution, or connectivity could produce effects that look like inconsistencies. What appears as a law breaking might be a system reaching its boundary. Some theories explore discreteness at the smallest scales. Space and time may not be smooth, but granular. If so, measurements probing fine detail could behave oddly, not because the universe is inconsistent, but because it is quantized beneath our expectations. Other approaches frame reality as governed by information flow rather than objects alone. In such models, conservation laws and constants emerge from how information is processed and preserved. This can explain remarkable stability, but it also allows rare deviations when conditions change. These ideas are not fringe fantasies. They are constrained, mathematical attempts to explain why known laws work so well and yet appear stressed. Each proposal solves certain tensions while creating new ones. Explanatory power is traded for complexity. For example, emergent laws can explain why constants appear tuned without invoking coincidence, but they raise questions about what enforces emergence itself. Discrete spacetime avoids infinities, but struggles with smooth continuity at larger scales. None of these frameworks claim to replace existing physics. They sit beneath it, speculative, but disciplined. Their appeal lies in their ability to unify disparate anomalies under a single intuition, that what we measure is not the base layer. If that intuition is right, it carries an unsettling implication. Systems with hidden machinery can fail, not catastrophically, but quietly, at thresholds we may not recognize until they are crossed. In complex systems, failure rarely arrives as a single dramatic event. It shows up as instability at the margins. Physics has its own versions of these quiet alarms, scenarios where the universe could be stable only conditionally, depending on parameters we do not fully control or even observe. One such case is vacuum stability. Current measurements suggest that the state our universe occupies may not be the most stable one possible. It could be metastable, meaning long-lived but not permanent. The probability of transition is extremely low, yet the concept itself introduces fragility into what was once assumed to be absolute. Another example appears in cosmological phase transitions. Early universe models rely on smooth changes as forces separated and structures formed. But if these transitions were sharper or more complex than assumed, they could leave subtle scars. Some anomalies may be echoes of those scars rather than present-day errors. There are also concerns about runaway behaviors. Dark energy, if not perfectly constant, could evolve in ways that alter cosmic expansion dramatically over time. Most models predict gentle change or none at all. But a small deviation, sustained long enough, would reshape the future of everything. These scenarios are not predictions. They are boundary cases explored precisely because the data allows them. Physicists treat them as stress tests, probing how much strain the current framework can absorb before it must be revised. What makes them unsettling is their silence. There are no alarms, no countdowns, no clear signals that a threshold is near. The universe could be perfectly safe by every measure we have, and still operate closer to an edge than we realize. This does not imply danger in any practical sense. It implies humility. Stability may be an emergent property, not a guarantee. And emergent systems behave differently when pushed beyond familiar regimes. At this point, the question shifts again. Even if we refine our models and patch inconsistencies, are we approaching a deeper limit? Not of technology, but of explanation itself. The phrase "reality is breaking down" does not mean collapse. It reflects something quieter. Across physics and cosmology, researchers are encountering points where trusted descriptions stop lining up cleanly with observation. Not everywhere, not dramatically, but persistently enough to demand attention. What began as a single disagreement about cosmic expansion widened into tensions about structure, timing, and stability. Each issue on its own remains explainable. Together, they suggest that our framework is under pressure, especially at its edges. The map still works, but its resolution may be limited. Importantly, scientists are not abandoning rigor. They are doing the opposite. These tensions are being examined with more precision, more skepticism, and more care than ever. Admitting strain is not failure. It is how progress has always moved forward. There is a difference between saying the universe is incoherent and saying our descriptions are incomplete. Every anomaly discussed lives in that gap. The data does not scream, it whispers, and only when listened to closely. This is why the moment matters now. We are not facing mystery because we lack tools. We are facing it because our tools have become sharp enough to find the seams. That is a sign of maturity, not confusion. History suggests that such moments precede deeper understanding. Newton did not fail because relativity arrived. Classical physics did not collapse when quantum mechanics emerged. Each framework remained useful, even as its limits became clear. The discomfort comes from uncertainty about what replaces the current picture. It may be a refinement, a deeper layer, or a shift in how explanation itself works. No one can say yet, and that honesty is part of the signal. If there is a lesson here, it is not that reality is fragile, but that certainty is. The universe continues to behave, even when our stories about it hesitate. Paying attention to those hesitations is how science advances. So the question to leave open is a simple one. As measurements grow sharper and models grow heavier, are we approaching a clearer picture of reality, or a clearer view of the limits of knowing it? And if the universe is still willing to answer, are we ready to hear what it actually says?